All right, welcome to module number 30. In number 29, we were looking at linear regression, and in particular, we were discussing least squares as a possible technique to perform linear regression. And now we're going to look at subset selection, where we want to perform linear regression, but we want the outcome, the model, to have a certain style. We want the model to be sparse. We want the majority of the coefficients, the betas that we've been talking about, we want them to be 0. And therefore, let's say that we have 50 explanatory variables. We want to only use, let's say, 5, 6 of them. So this is a special type of linear regression. And we'll discuss how least squares is actually suboptimal for this sort of problem. So there are other approaches. And we're also going to be seeing an example that illustrates where this can be interesting. All right, so overall, least squares often outputs an entirely non-zero vector. The reason is that we have recall that we have, and I'm going to annotate this, we have y equals x times b. B is beta plus, I'm just going to call it n here. Earlier we called it epsilon on a few of the slides. And beta is going to be x plus meaning the pseudo inverse of x multiplied by y. All right. Now, because of the noise, y is a vector, of course, and it's often kind of messy, in quotation marks, because, again, because of the noise. So let's say that there might be 7 different values, 7 different possible values that you would expect, but the noise kind of gives you more. It makes it noisy. So now you multiply a noisy y by the pseudo inverse x plus. And the outcome is going to be entirely non-zero. However, we're saying that in subset selection, we do want the beta vector to have many zeros. So we want a sparse beta vector. All right. So why do we want it to be sparse? It's more convenient for the human operator in many applications to interpret a simpler model. So suppose you're a cardiologist and you have a person coming into the emergency room with some heart problem, or it seems could be a heart problem. And you have hundreds of variables. The healthcare system or insurance company, whatever it is, has tons of data on this person, and you, the cardiologist, can access this data. But you know, you're in a rush. This person is in bad shape, and it's very difficult for you to look through 500 numbers. Not to mention that as a human, it's impossible to perform like a remotely optimal decision when you have hundreds of numbers. Like it's impossible to perform this type of calculation. Instead, maybe you're comfortable with 5, 6 variables. So what we'd like the beta vector to be sparse, and because of that, there will be a small number of non-zeros, and we're willing to accept a slight loss of accuracy. So whereas a completely non-sparse beta might lead to more accuracy in your model, as long as you have a modest amount of accuracy, but the human operator feels comfortable with the model. So let's say the model shows these 5 variables, and the model says, look, based on these 5 variables, it's not a heart attack, it's something else. And now the cardiologist who's familiar with these 5 variables, they look at the 5 variables, they're like, yeah, no, I agree, it doesn't look like a heart attack. But on the other hand, if they had to use all 500, so maybe the software can tell them, based on those 5 numbers, the probability of heart attack is 11%. And based on the entire model, it was 8.5%. So yeah, I mean, there's some disagreement between the simpler model and the complicated model, but no, we don't think that there's a heart attack. So then the physician looks at those 5 numbers and says, yeah, it doesn't look like a heart attack to me, I agree. And they move on and they they continue their work. So bottom line, least squares, why does it return this non-sparse vector? Again, we're just multiplying a matrix by a non-sparse. The non-sparse vector y is multiplied by the vector, the pseudo inverse of x. And least squares doesn't use possible knowledge about the structure of beta. So beta could be sparse in this problem. It could be discrete valued in a communication problem that we're soon going to describe. It could be non-negative. It could be plenty of structure. Least squares doesn't know that. All it does, it multiplies a vector by a matrix. That's it. And if you add in this extra knowledge about the possible structure of beta, you might do better. That's the key point. So least squares is a linear method, linear because you multiply by a matrix, but it is suboptimal. All right, so let's clear the drawings and move on. So here's an example. Consider a communication problem. You have n users, and most of the users are going to be inactive. K out of the users are going to be active. K is much smaller than n. And each of the active users, maybe they transmit a -1 or a +1. The inactive ones, of course, they're not transmitting. They're transmitting a 0. So now, what you have, let's think about it. You have y, which is a vector, is going to be a matrix X multiplied by a beta vector where most of these are zeros, and you have, let's say, just these two non-zeros. Now this guy corresponds to this column, and this guy corresponds to this column, plus noise. But what I'm saying, you have the noise is added to a superposition of two columns. These two columns are multiplied by -1 or +1. All the other columns are multiplied by 0, so we can forget about them. So the communication channel is often modeled as linear. Again, as we've discussed, many things, definitely an electromagnetic channel, are not precisely linear, but oftentimes it's close to linear. Y equals hx plus noise. X is this vector of -1s and +1s, but it's dominated by zeros. So I called it beta, it could be x. H is a matrix of a waveform that each of the users might be transmitting. There's noise, of course, and y are is the overall waveform transmitted over the channel. So now, what does least squares do? Least squares multiplies the y by the pseudo-inverse. Could be, depending on your notation, the pseudo-inverse of x, the pseudo-inverse of h. But y, because of the noise, is containing a variety of numbers, and you're just multiplying it by a matrix. That's it. So h pseudo-inverse y contains elements not among those three, -1, 0, +1. But we want our output to be primarily 0 with a small number of -1s and +1s. And if a phone system is aware of this structure, it can, of course, do much better. So in subset selection, again, we want a sparse beta. We select a subset of columns of the matrix X that approximate Y well. Again, this can be in a machine learning type of problem where we have data, we want to model the data, we want a reasonable model, and for a human operator, we want a sparse model, a model that has few elements to work with. Or it could be a man-made type of data, a communication problem, where we design things especially to be close to linear, and now we're working with that, and we know that the underlying transmissions are -1, 0, and +1. Again, primarily 0. So it could be just data, or it could be a man-made type of problem, but either way, in both problems, we want our output to be primarily 0. This is called subset selection. Subset selection because we want a subset of the columns of the matrix. In general, it requires combinatorial complexity. If you have, let's say, n columns, and you want to select k of them, then you have k choose n possible sets of columns to examine. That's a very large number, astronomically large. Various techniques provide faster runtimes. Some of them offer near optimal outputs. So they approach the best solution, but they may not find it, or they may be, perhaps the quality of their solution is going to be very close to the quality of the best solution. What we're going to do in the sparse signal processing module, or rather segment of this course, we're going to look at fast algorithms for doing this. However, they require the elements of the matrix to be independent and identically distributed, IID. In some applications, that's a realistic scenario, a realistic assumption. In other applications, it's very far from the truth. So in a nutshell, what I'm saying, under some assumptions, you can do well for subset selections. Under other assumptions, you'll pretty much be running heuristics. Okay. Another real-world example is as follows. You have a medical setting. Columns of X are measurements relating to patients. Again, you can imagine a cardiologist or something. The height of the patient, blood pressure, heart problems in the family, etc. And Y is the medical problem that we're trying to predict in the testing data, and of course learn from in the training data. So for example, maybe we want to predict the blood pressure, the sugar level, the treatment costs. Imagine that you're an insurance company and you really want to know who are the potentially expensive patients. Let's say you want to find a way to reduce their costs. So trying to understand this will be interesting for you. And we want to understand the relations between the various conditions. And if we can understand those relations, hopefully we can provide better health outcomes. Hopefully we can do so using fewer medications, less treatment. So this would basically save the health system money. Now, there are a lot of columns. There are dozens or hundreds of columns, maybe even more. And because of that, it's difficult for the physician to comprehend the linear model, as we were describing our cardiologist friend earlier. And subset selection is going to allow the cardiologist to consider a model with a small number of terms. And again, it could be that you're going to give the human the correct answer, the optimized answer based on all the information. You're also going to give them the simplified answer. And if there's a significant disparity of the two, it's a judgment call. They can, it's their decision what to do. But most of the time, the two predictions are going to be close, and they're going to be very comfortable going with 4 or 5 factors that they're comfortable, that they're very familiar with. All right, so that concludes module number 30, and we'll continue next time.